So thank you. Okay, I can start sharing.
Looks good.
Do you see? Yes. Okay.
Yeah.
Let me hide my screen. Okay, good. Okay, so I think we can start. So thank you for inviting me and giving me the opportunity to tell you about this LEMMA proposal. So I will start describing you how the LEMMA concept is started and the status on the accelerator studies that we have performed so far, with some future perspective that could be done. So LEMMA stands for Low Emittance Muon Accelerator and is a concept based on a positron-driven source for muon beams. The idea is to produce muon beams in positron annihilation on electrons at rest. As I will show you, the most feasible option that we have seen is to have about 45 GV positron beam hitting on a target. So this would allow, and the strength of this idea is the possibility to have a low emittance muon beam, which would allow to overcome the cooling. Also permitting to have, in principle, let's say, very high center of mass energy muon collider. On the other hand, LEMMA has to deal with the low muon rates due to the low cross-section. As you all know, the standard way to produce muon beams is from protons on target. And just to remind you that this implies that these muon beams have a very high emittance at production, so the cooling is needed. On the other hand, if we produce it from a threshold in asymmetric collision, already when we published our first paper, the first reviewer, let's say, acknowledged the fact that this could really be a breakthrough because of the low emittance intrinsic in the production. You have perhaps seen this figure where there is a comparison of the map scheme with LEMMA. Of course, it's not really a fair comparison, as map studies are much advanced, but the message here is that in principle LEMMA could be much simpler, because we would just need a very intense positron beam, which could be stored and hitting on a target, and then the two muon, mu plus, mu minus, produced would need to be accumulated and accelerated and sent to the collider just as for map. Of course, there are some key aspects to be fully studied and to prove the feasibility of this concept, and I will try to go through let's say our thoughts and our studies. But just let me spend one slide saying that also MAP has to deal both with the muon rate, and in fact there is a combiner ring, a combiner that is needed to simultaneously deliver multiple proton beams on pion target to provide the required production rates, and a huge 6D cooling factor is needed to reach the goal value of the order of 10 to the 12 muon per bunch that is necessary to reach luminosities foreseen in the order of 10 to the 35. And so this cooling is really the the let's say the key R&D, the key topic that has been studied and tried experimentally also on mice for many years, where I think a couple of years ago they published this paper showing that they could prove a reduction of about 10% emittance, but still you understand there is a long way to go to prove 60 cooling and small emittances. And on this, the MOAN collaboration, international collaboration group that is forming after the strategy is focusing to continue the study on the cooling. But now let's go to the LEMMA. LEMMA would have the advantage, as I said, to have a very low emittance, and the beam divergence could be very small, close to the threshold. This also the luminosity with low emittance would allow to have low background of the low neutrino radiation, and so also easier experimental conditions, and in principle we could go up in energy. We could have reduced losses from decay and a small energy spread. Unfortunately, the cross-section of the plus and minus into mu plus mu minus is at most 1 microbar with respect to the one from protons that is of the order of millibar. So this is what we really need to optimize the production, the muon production rate. The possible implementation to produce muons in this way, when we started to think how to do, at the beginning we thought, okay, we could have a low energy collider with the plus and minus beams, but both conventional asymmetric collisions and a positron beam interacting with a continuous beam from the electron cooling were not feasible. So we also made some simulations of a positron beam on a plasma target, but the required density of the plasma is not in the orders of those that are possible. So we investigated, and this is the scheme that we use for LEMMA, to have a positron beam on a standard target, eventually with crystals in channeling. And this means that we need a 45 GeV positron beam hitting on electrons at rest in a target. And in this way, the let's say the muon beams produced would be dominated by the emittance of the positron beam plus the contribution due to multiple scattering and the Bremsstrahlung and so on. So the muons have a gamma produced at a gamma of about 200, and the laboratory lifetime is 0.5 milliseconds. So the contribution to the muon beam size, as I said, is dominated by the positron emittance, and the contribution to the and we have the length of the target that contributes to the production angle. So the muon beam at the exit of a 3 millimeter beryllium target, we have verified with this simulation that is just the same of the positron beam, assuming let's say a pencil positron beam, let's say neglecting the scattering contribution. So which are, let's say, oh sorry, I wanted to take out, yes, this. The criteria for the target design let's say, is the following. We want to optimize the luminosity, which is proportional to the square of the number of muons per bunch, and is inversely proportional to the muon emittance. So we want at the same time to minimize the emittance, but have the highest muon rate. So this is, we have to find the best trade-off. If we consider heavy materials with thin target, then as I showed you, the emittance is proportional to the length of the target. In this way, we can minimize the emittance. But if it is a heavy material, we will be dominated by Bremsstrahlung. And so in the end, the muon efficiency, the muon production efficiency is in the order of 10 to the minus 7. On the other hand, if we have a very light materials but thick target, we will need long targets to produce the same rate of muons. And so the efficiency is 10 to the minus 5. In the end, the best trade-off is with not too heavy materials like lithium, beryllium, or carbonium, where we can have a small muon emittance with small positron loss due to Bremsstrahlung. So we are in the order for the muon conversion production to the 10 to the minus 6. And which are the possible schemes for this muon production? We need, as I said, a 45 positron beam impinging on a target. What we have studied is the possibility to have a target inside the 45 GV positron ring, and in this way we could reuse the same positron beam multiple times until it is lost, and then the muon beams would go into accumulator rings and accelerated. On the other way, and in this case, we need a thin target, of course, because we don't want to perturb so much the positron beam. We want to reuse it. On the other hand, we could think of having a storage ring, 45 GV, where the beam is then extracted and sent to this muon production target that can be a thick target, and with the advantage of increasing the muon production, but at the expenses of the fact that we cannot reuse the positron beam easily, only once, unless we design a recovery system and try to reuse it. But on the okay, so we have designed the rings and the system for the target in for both cases, and try to see let's say the possible the pros and cons for the two systems. For the multipass scheme, what we need in order to have interesting luminosities, we need to have at target order of 10 to the 11 muons per second, which means a very intense positron beam. 10 to the 18 positrons per second is needed at the target, and this brings to the challenge of designing a low emittance and high momentum acceptance ring. And on the other hand, we also have you can imagine a order of 100 kilowatt class target in the positron ring for the muon production, because we will have the same many bunches heating on this muon production target, single, and it has to be thin enough not to perturb the positron beam, and so we will have a very large energy deposition density. In any case, in order that this system works if we have a high energy acceptance positron ring, and so also we need an intense positron source rate, which has been evaluated to be in the order of the LHEC-like positron source. The other two points is the high rate positron source, as I just said, but also the high momentum acceptance muon accumulator rings, which is also needed for the single pass scheme that we have designed, and I will show you. So this is the low emittance 45 GV positron ring with a circumference of 6.3 and 27 kilometers, with the idea of reusing existing tunnels for different emittances. And in this ring, we have then added a target, 3 millimeter beryllium target, and performed a particle tracking simulation to check the emittance growth, the positron emittance growth, and we have verified that if we lower the beta at the target and suppress dispersion values at the target, we can control multiple scattering and Bremsstrahlung. So let's say to summarize the comments on this multipass scheme where the target is inside the ring, what we see is that unfortunately we have to then deal with the high power on target, but we would also have a low number of muons per bunch, and the muon beams is produced almost in CWs, and this also is not compatible with then further acceleration by synchrotron. The main advantage is that the muon emittance in this scheme is small, is the best that we could get, but we have to deal with these other topics. On the other hand, we then consist that, okay, let's see and make a comparison with the other possibility where we have a positron source, the ring, the positron ring, but now we can think to place the muon target outside the ring with eventual extra delay lines in order to increase the number of positron bunches and increase the muon rate. We considered a thick target where the positron beam passes only once through, let's say, of the order of 1x0. I will show you that we have optimized this value, and so we obtained more muons produced per bunch, and also the power can then be distributed over a long target. We have designed the muon accumulator rings with a very large energy acceptance, and this allowed us to perform start-to-end particle tracking from the production at target, then accumulating, and this allowed us to make a realistic estimate of the emittance and the number of muons per bunch, and we considered solid, liquid jet, and compound liquid solid targets to see which one, let's say the different characteristics. Let me mention, and before showing the results on the muon accumulation in the rings, let me make some consideration about the accumulation. So we need the accumulator rings to be as short as possible because of course muons decay, and we want to perform this stage in the fastest possible way, and we also want the largest possible energy acceptance in order to keep all the produced muons. The number of muons increases by using a thick target, because okay, but as if the target is too thick, then the beam size will increase. On the other hand, we also know that the multiple scattering contributes to emittance also as a square root of x con 0 and the number of targets in the accumulation. So it's a matter of finding the best trade-off. For the beam, to decrease the length of the target, we have considered the possibility of using multiple IPs, but from the optical design point of view, in the end, the emittance of the moon beam in the end was really too large. While to control the multiple scattering, one possible solution is to use spaghetti film-like targets or channeling crystal, where the positron bunches are transversely smaller than a liquid, for example, a liquid hydrogen film flowing at constant velocity. And in this way, we think that this could be an R&D that could be interesting to perform, to assess the feasibility of this design. So what we see in this upper plot is that the divergence of the moon beam increases as a function of the accumulator turns, and in the end, at the end of the accumulation process, if we start from, let's say, even if we start with higher beam divergence, in the end, this will be smeared. So, because you see, if we can increase the positron beam energy, the moon production will increase, but we also have, on the other hand, the energy spread will increase and the beam divergence. So we have to keep in mind all these values to find the optimal working point. Now, on the target options, the material, of course, plays a crucial role. The lighter the material, the higher the production efficiency. And what we see is that for most of the muons are produced in the first 3 targets. If we consider, for example, in this simulation, 10 targets with 0.1 x con 0, and roughly at 0.3 x con 0, let's say we get most of the muon production. We focused our studies on the liquid lithium and beryllium. So if we compare the behavior of beryllium and liquid lithium in terms of beam size, divergence, and muon production as a function of the positron energy, what we see is that beryllium has a less increase of the beam size because we will need a thinner target. The beam size is proportional to the thickness, while divergence depends mainly on the positron beam energies dominated by the production kinematics, so we don't see really a difference. And this is the production efficiency, where it is slightly better with the liquid lithium. We then, after these studies, we said, okay, we also needed to optimize the target choice, solid versus liquid, also considering the accumulation process. And so this is the ring that we have, that has been designed with a compact 140 meters circumference with 15 Tesla dipoles. very important is the high energy acceptance, which in this design that is based on the new low emittance synchrotron light sources, which has been designed by Pantaleo, we have an energy acceptance as large as minus 10% and plus 15%, as you can see in this plot with the muon beams captured in the ref bucket. So this has been possible thanks to the very good correction with the dedicated families of sextuplets. And so this is the alpha ring, about 70 meters, and the insertion target, the insertion region for the target with the central cell. Now, with this lattice, we could perform particle tracking to see the accumulation process, how at the end, the muon, the number of muons per bunch that could be extracted from these rings. And we considered the beryllium target and the liquid lithium for the same radiation length, but of course for beryllium it's 10 centimeters, while for liquid lithium is almost half a meter, 45.6 centimeters. And what we see is that for beryllium, the beam size increases a lot, and the accumulated muons at the end of 1,500 tons is about 3.5 10 to the 18 muon. It is efficient for the production, but the muon beam size and divergence increases due to the multiple scattering. On the other hand, if we consider a jet of transversely 50 microns, which is smaller than the stored beam size of the order of 1 millimeter, in this way we can mitigate multiple scattering and have a higher, by a factor 30, this value that is proportional n squared to the emittance, which is proportional to the luminosity. But so the disadvantage is that it is really a long target. So what we considered is a possibility to have a compromise with liquid lithium, 10% of liquid lithium plus 90% of diamond. In this way, the jet target would be in a liquid state, suitable to be film jet, but the length could be reduced. Reducing the length of the target, we could also reduce the beta star at the target. Of course, we don't want the hourglass effect, so we need the beta star has to be below the target length, and this allows to increase the muon production, to keep the to decrease the emittance. So the best solution is that we found is a 50 microns of liquid lithium diamond film jet target with 0.5 x(0) corresponding to 6.7 centimeters. With a beta star of 10 centimeters, that would give a number of muons per bunch of 0.4 10 to the 9 and an emittance of 0.3 microns after about 1,000 tons of accumulator in the accumulator rings. Further optimizations could be imagined increasing the accumulator rings energy acceptance that would allow to increase the number of muons produced, thanks to the fact that we have an increase in the cross-section. And for example, a factor 2 could be obtained going to a 50 GeV positron beam. And also reducing further the beta star would reduce the final moon emittance. Up to now, we didn't manage to design, let's say, the final focus with lower than 10 centimeter, but it could be an optimization work to be done. So another factor of improve could be obtained if we consider the multiple positron bunches hitting on the same target using delay lines, what we have called revolver configuration, that would allow to further increase the muon production, reaching the value that is our goal value for comparable luminosities to the map scheme, we would need 10 to the 9 muon per bunch with an emittance of 0.1 microns after 200 tons. And you can see here the comparison of the accumulated muons compared to the, let's say, with 7 impinging positron bunches compared to the single bunch, and also the increase in of this parameter n square over emittance. Now, just I'm about to conclude on the, let's say, just mention the fact that perhaps one of the key topics of this scheme is the target, of course, the muon production target. So we aim at a bunch of 5, 10 to the 11 positron with a very small transverse size of the order of 10 to 20 microns. To have a low emittance, but this poses problems on the temperature increase. We have seen that this kind of small spots are not sustainable due to the temperature increase, and so some thermal studies have shown this, that the temperature increase is not sustainable, but if we consider the possibility of using rotating targets, then the temperature increase, you can see in the simulation, is dramatically reduced, and so resulting in principle to acceptable values. And this is like was designed studied for the ILC, where there was the design a rotating target. This could allow, because if you have, of course, a rotating target, you can have power removal by radiation cooling. Also at PSI, they have this kind of system. So the other point of LEMMA is that we need an intense positron source. This is a very intense source that we need, but this kind of R&D is already performed for other E+ E- future projects. And these are some estimates that we have done in comparing you see the LHEC pulse, the value that is needed, and what we would need to go beyond that, but okay, this is the other point. So in fact, the potential key R&D items I tried just to list, to summarize, is the beam production is the target complex. I did not mention the accelerator complex design for the fast ramping magnets, high field superconducting magnets, which is actually an R&D that is performed also for other projects, like for example the FCCHH, or then the collider ring design with the radiation hazard, which is, if the emittance is not so low, is the limit of the muon collider. What is interesting is the possibility of reusing existing infrastructure or consider also synergy with future projects like reusing the FCC tunnel. And so this brings me to the conclusion, that is that, okay, there is no easy solution to high energy and high luminosity muon collider. I think that LEMMA is an elegant concept combined to state-of-the-art high energy acceptance and low emittance rings, aiming at good quality muon beams. The ultimate performance of a muon collider based on this concept is mainly dominated by the muon production target and by the quality and intensity of the positron beam. And so the R&D that is needed would be mainly in the high power target and the high rate positron source. And just let me mention that an FCC MUMU to follow FCCE and FCCHH seems an attractive option worth to be investigated. Okay, thank you.
Thank you, Manuela. So this is a dual seminar, right? We still have Marco's seminar coming up shortly,
Yes.
but I think if we can ask a couple of questions, it's okay, I suppose now, right? So if there are any questions for Manuela that we should address now, we can do that. Otherwise, we can also, I think she'll stay till the end of the event, so we can also ask her later after we talk to Marco. So open for a few questions, couple of questions now. Go ahead, Varun.
Actually, I have a very naive question. Maybe actually I joined just a few minutes late, so maybe I have missed on that. It's mostly on your slide 20, where you talk about, you know, comparing different materials for production efficiency. Yeah. So here, when you, what's actually how the production efficiency is defined? Like you use the same number of initial muons, and do you get this? Do you also like the energy of the muons also changes, or like how the production efficiency
no,
is
so
defined
let
here?
me see. I think I defined here actually is the number of produced muons as a function of keeping constant the number of the positrons produced. So the number of produced muons let me sorry, I don't want to let go here. So the keeping constant the positron energy, we look at the quantity of the number of produced muons. So the number of produced muons versus
So this is integrating over certain emittances of the muons coming of the positron beam growth, right? The emittance grows differently, you said. This is for a fixed emittance growth?
Yes, so this is for a fixed positron emittance, and for a so 3 10 to the 11 positrons at 45 GeV with an emittance of 0.7 nanometers go through a let's say different thickness for different materials, and we see how many muons are produced.
So each of those will have a different emittance growth for the beam as it goes through the material, right? I'm assuming that we're not going to have...
Yes, okay. Yeah,
okay, got it.
Sorry,
Well,
yeah, I didn't understand.
Matt,
you have another question. Matt?
So maybe I missed this as well, if you comment on it, but you know, the energy that's needed for this threshold reaction, 45 GeV, is very suggestive. So you compare the positron source to, I think, like an ELHC sort of collider. How does it compare in terms of the positron production to a GigaZ proposal?
Sorry? I'm not sure I understood the question.
For a GigaZ machine, there is a positron beam needed. I think you had a slide which shows the positron counts per bunch somewhere, right?
Yeah.
Comparing different colliders.
Yes, for the positrons.
Positron Yeah.
Yeah, so I was wondering in terms of how many positrons are produced, how it compares to a giga-Z.
So is this one that we are comparing the positron source?
Yeah, I think that what you need is FCCE number for the E plus per second. That's also around 10 to the 14 per second, right?
Yes.
In the FCC positron beam.
Yes, even if the positron source, so I'm not sure, I don't have here the number. I should check the number of the positron because the positron beam is, okay, we have 10 to the 11 positron per bunch. But this positron source, I don't have the number now. I should check.
I was just wondering because, you know, it seems like a natural thing to do to either before or after using this as a LEMMA machine to use the positron source to drive a giga-Z at very high luminosity.
Yes, yes. Ah, okay. No, because I didn't. Yes, of course. Okay, I didn't understand what you. Yes, in fact, you mean the 45 GV positron ring could be, in fact, the ring of the FCCE at the Z. Yes, this is, in fact, an interesting synergy that we have been considering.
You do need the electrons also, but okay.
In that case, yes, but yes.
So electrons are a little easier, yeah.
Sasha.
Yeah, I have maybe very simple question. Sorry for my ignorance. Do you care about this target? Do you care about the spread of the energy in the initial muons or not? I mean, when you are producing these muons, do you care about the energy spread or not at all? Because I think that for different targets, you may have also different energy spread, no?
Yes, you are right. Okay, I didn't mention very well, but yes, you are right. In fact, it is true that we consider the energy spread of the muons, and we know that it increases with the energy of the positron beam, and this is also. And so this is the trade-off that we have to find. We don't want to increase the energy spread. We would like to keep it as small as possible, but then we increase the cross section. So we have two competing. Yes. So we look at that. Yes. Because also if we go to a higher positron beam and the energy spread is larger, then the energy acceptance of the accumulator rings will have to have a larger energy acceptance also. Also the quality of the muon beam decreases.
So let's stop the questions here and move to Marco and come back to it. Looks like our seminar will extend a little bit beyond the 1 hour, but that's probably okay. All right. So Marco.
Okay, let me share slides. Give me 1 second. Where is that? I need to find my slides.
Thank you, Manuela. I forgot to say that.
Can you see the shared slides?
Yes. Oh, okay. We see your share screen. Can you?
Okay. So let me try to do it better.
Oh, you just swap this place with it.
Is it better?
Yeah.
Can you see that?
Yes, that's good.
Okay. So again, thanks for the invitation. It's a pleasure for me to talk to so many friends. which unfortunately is some time that I haven't seen in person. I hope to get the chance to see you soon, or maybe at CERN, not too late. So indeed, this is a proposal for an experiment to test essentially the process which is at the base of the LEMMA scheme. Okay, so it's always good to test things in advance, even though, let's say, the process itself, let's say the dynamics of the proposed experiment is far from what LEMMA requires in order to produce a very brilliant muon beam. But anyhow, setting up something that allows producing muons in the same way as LEMMA is aiming at, we believe it was worth it, and that's why we started a campaign of measurements, I think 2017 or something. And then, let's say, after a couple of tests, essentially we learned enough in order to propose an action experiment to do a proper set of measurements. Okay, so let me try to go for that. The thing is that at the moment, in order to reproduce what LEMMA requires in terms of a positron beam, we would need a dedicated machine, which we don't have at the moment. As you know, there are no 45 GeV electron-positron machines at the moment anymore. There were in the past, which is quite kind of funny, but there are no more at the moment. Still, we can get 45 GeV positrons and electrons, but as tertiaries from proton beams. Okay, so the only place nowadays that can provide such a tertiary beam is essentially the north area at CERN, where you know that the SPS beam gets extracted and shot on target, and then out of the many products of the decay products, you can stream away a positron beam, okay, and tune the energy of such protons such that they match the requirements of the users of the area. Okay, so before proceeding, let me stress the fact that there are several other experimental tests that can be conducted on the LEMMA scheme. Manuela mentioned a few, especially on the targets and their thermomechanical endurance, and then also on potential storage ring for the positrons and so on and so forth. But those are not going to be discussed here. So essentially, what I'm going to discuss is what we call LEMMA TB, essentially LEMMA test beam, whatever, in order to with the goal of testing the LEMMA production scheme. So we listed a series of goals, okay, which are summarized here essentially. So these processes are not science fiction in a sense that they can be simulated, but of course you also want to measure things in order to actually assess the actual numbers. Okay, so giant is good, but having a direct measurement is always good. So indeed, the main selling point of LEMMA is the tiny muon beam emittance, and therefore you want to assess how small that is. Okay, let's say really measuring that. And then Manuela showed as well the very many dependencies that are there on the properties of the muon beam on the positron beam kinematics and properties. And therefore, assessing those dependencies is also very relevant, okay? On the spot size, on the energy spread of the positron beam, on its divergence, on the target thickness, on all these kind of things. Okay, so trying that in a lab, I think it's we believe it's very relevant for supporting the LEMMA scheme, or let's say assessing whether it's indeed all the calculations are actually trustworthy. Then some schemes implementing the LEMMA idea requires the positron beam spent on the target to be recovered. Okay, so something that we can also try to study in such a setup is the properties of the spent positron beam. So indeed, the idea is to shot 45 GeV positrons on target, and in addition of the study of the muon pairs produced that way, we can also try to see what happens to the rest of the beam that did not produce the muon pair. Okay. Then, of course, there are also some physics measurement that you can try to assess. This is the plus and minus. To be plus and minus probably is the one process that every student, studying quantum field theory is asked to compute at least once in a lifetime. But you need to remember that that process is always computed at, in the relativistic limit. Okay. Whereas now let's say we are dealing with the process at threshold. Okay, so essentially two muons are produced, okay, basically at rest. Okay, and funny enough, at least we haven't found any. There are no measurements at threshold. So that would be the first time that such a measurement is performed. We don't expect surprises, even though there are possibly weird QED effects that could be interesting to be assessed. And actually, there is also an idea, even though we are aware of the fact that it's kind of tough, but we know that if you are close to the threshold, but actually below the threshold, you might actually produce true muonium, so a coupled, a bounded mu plus mu minus state, which is never been observed as far as I understand. Okay, I think the muonium, meaning the bound states made of muons and electrons, or let's say mu minus and a positron, or mu plus and an electron. I think that's been observed, but the true muonium, the mu plus mu minus bounded state, has never been observed. Anyhow, so moving back, so as I said, I already mentioned this. This is just a picture of the north area at CERN. On the left is let's say a pictorial view of the area. On the right, there is actually a snapshot of one of the lines, actually the one where we had our experiments in 2017. So the idea, as I said, the idea is to get from that line a 45 GeV positron beam. So the thing is that is a tertiary beam, right? So the problem is that such a beam is really far from what would be needed in order to produce an high intense and low emittance muon beam, right? Because it is true that the emittance of the muon beam is small, but is, let's say, is slightly larger than the positron beam emittance. So given the fact that typically the positron beam can be squeezed down to microscopic scales, therefore you expect the muon beam to be as small as that one. But if you start off with a positron beam which is large, which has a large emittance, then of course the muon beam is going to also have a large emittance. Okay, so the direct measurement of the muon emittance is something that okay, it's interesting anyhow, but something more about that has to be done, given the fact that with a tertiary beam you cannot expect to have a very competitive emittance. Okay, and also the number of positrons that you can get per spill is not that much. We expect typically they can give us of the order of 5 millions, or let's say 10 millions, up to 10 millions positrons per beam. Okay, and let's say that comes from the extraction of from a continuous extraction of the proton beam from the SPS, and typically they manage to do that. They manage to do a cycle of extraction every 30 seconds or so. So we do expect a structure of the beam which is made of roughly 1 megahertz of positron on target for 5 seconds. That's the spill, and that thing is repeated twice per minute or so. So if you compute the numbers and you plug in, let's say, 0.1 x0 beryllium target, which is the one we are using at the moment, you expect that a ridiculous number of muons, but still just to give you a measure how much how tough is to get a high number of muons these ways. So with the 5 millions, essentially 5 million muons per spill, we expect 5 sorry, positron per spill, we expect 5 muons per spill. So an efficiency of 1 in a million, more or less, okay? So we aim at measuring these 5 muons, muon pairs, of course, per spill. So that's a drawing of what an experiment could look like. Essentially, you have an incoming positron beam, then you have tracking devices before target and after target, so to measure the incoming positrons and the outgoing muons. After the tracking devices, you do want to place a magnet, a dipole magnet, in order to split the plus and the minus charged particles, especially the mu plus, mu minus. So again, you place tracking detectors, but then afterwards you want to essentially tag the particles emerging, depending on whether they are positron electrons or muons. Okay, therefore you place an electromagnetic calorimeter, then you have some shielding, and then beyond the shielding you have the muon chambers. Okay, so now I'm going to describe you the challenges that are there. So indeed, I explained you before that the emittance of the north area positron beam is very large. Therefore, if you want to measure something which is useful for assessing the LEMMA properties, we want to measure the intrinsic emittance due to muon kinematics. Okay, so we want to measure what acts on top of the positron beam due to the kinematics of the muon production. Okay, so if you want, that's very challenging because indeed, I mean, the emittance is very large, and you want to measure a small correction to that if you want. In order to do that, we need to track every single particle, and then if you want, construct the emittance a posteriori by placing a single point in the usual emittance plot. In order to do that, we need to track very precisely the incoming positrons and track very precisely the outgoing muons. Okay, so this requires, first of all, to track the particle, the incoming particle one by one, and also we need a very, very good tracking resolution before and after the target. So I also already mentioned I got something on the chat. I mentioned already the fact that we need to track every single particle, and therefore we need essentially at that time less trigger and the DAQ system. Okay, and also we need to essentially dig our signal out of a very large background. Okay, and if we want to assess and measure the cross section, we also need full control on the trigger efficiency and the vector acceptance. Okay, and possibly we might also need to have candles in order to say normalize the luminosity. Okay, so for instance, the gamma production, which would require a dedicated calorimeter, because of course the gammas would move straight forward with respect to the beam line. Okay, so the PAX experiences, as I said, we had, so that's a picture on top of our setup, which is, okay, that one has been taken, that picture has been taken from the setup we had in summer 2018. The location is the same one as the CMS HCAL is typically tested in the north area. So the system is very much similar to the sketch that I showed you before. Okay, with silicon detectors for tracking around the target, then with the dipole magnet, again with the silicon stations afterwards, a couple of calorimeters, and then the muon chambers. Okay, the thing is that, as we said, that that has been done with essentially zero budget. Okay, so you're talking about a few something like 20-30K kilo euros essentially for the whole thing. Okay, because we reused components that were available back then. Okay, the goal indeed was not to provide super duper measurements, but just to learn and get to know what are the issues in order to perform the actual measurements, okay? And also the amount of beam time that we got was very limited, essentially 10 days in total. Still, we managed to get some data, and the data looked reasonable to some extent. So we managed to, so from the plot that you see up there, that's the reconstructed beam momentum from the mu plus mu minus events, and as well as the invariant mass, which indeed matches the dimuon mass. Okay, so we published that on GINST. Okay, of course the emittance plots that you see on the bottom are somewhat poor, and given the fact that our system were not both from the tracking point of view and also from the trigger and the IQ point of view was not good enough, we didn't manage to have this correction event by event for the actual intrinsic muon beam emittance. So we learned from that experience, and we designed an experiment that was scheduled last year, but due to the pandemic, we didn't even started working on that. So we plan to do that next year. Actually, it was planned for this year. Actually, it was planned for this very moment or something like that. It was planned for October, November 2021. And I must say, the whole thing is rather ambitious. Okay, so we do want to have pixels, so the CMS pixel actually, around the target. So 6 stations, 12 modules. So essentially 2 modules per station, and then we plan to have 4 gem station, 1 before the magnet and 3 after the magnets. Okay, then calorimeters. Again, the idea is to use the CMS ones, and then at the end we're gonna have muon chambers, which I was gonna mention in a second. They are gonna be they are actually smaller version of the CMS drift tubes. The whole thing, of course, needs to have an improved DAQ system. Okay, the one we used in the previous setups was a cheap one with a very high dead time, and therefore was not good enough to have this event by event system. Now we do plan to have essentially a triggerless DAQ system, at least for part of the system, part of the detectors. Okay, and explicitly with essentially 0 dead time. So we submitted this proposal to the SPS scientific committee, which very much appreciated the idea, and they would have been ready to provide beam time also this year, but as I said, we didn't have the chance to work on this thing because of the pandemic. So everything is postponed. So now let me go through the various components. So the one that's been used also in the past are these detectors here, the drift tubes. So essentially we are using, this is a picture that I took in our lab here close to Padova. Essentially there are smaller versions of the CMS drift tubes equipped with the electronics for phase 2. We have 8 2D chambers, 2-dimensional chambers, let's say chambers that measure 2 dimensions, and like those can be coupled in order to measure 3-dimensional tracks. We actually employ a system that based on FPGA boards mounted on the PCI bus of standard servers that can allow reading out data at, let's say, continuously at 40 megahertz. Of course, we use the same clock as the LEC clock, just because all the electronics nowadays works that way. We also have dedicated online reconstruction, which, if you want, is similar to the trigger reconstruction implemented on this FPGA. So those are ready to go to some extent, and they worked already in the past. Okay, these I can skip. Essentially, this is just to depict the online processing pileup that we have, fully triggerless. Then we have our colleagues from again from INFN that work also in CMS in the GEM community, they are producing dedicated 10 by 10 triple gems, okay? And in addition to those, we're gonna have also standard CMS modules in the, let's say after the magnets, in the two arms, okay? And they are also, they also have the possibility of reading out the chambers continuously, meaning like at 40 megahertz without an explicit trigger, okay? Now coming to the trickiest part, which are the pixel modules. So these are standard phase 1 CMS pixels, okay? Pixel modules. They are the same one that are used in an experiment which is called CHROMI, which is also in the north area, just in another beamline, and is the one that is used. It's essentially they make up a telescope that is used in order to qualify the silicon strips for the phase 2 CMS tracker. So these pixels, they are used as telescope to track the incoming particles, the charged particle, that are used in order to qualify and test the new silicon strips modules for phase 2. Okay, so that's what CHROMI is about. The thing I'm mentioning this because essentially the setup that we aim at using is essentially the same as CHROMI. Okay, but we would like actually to get away with the, let's say to move away, sorry, from the legacy electronics that is currently used in this setup, which is essentially the old CMS, the CMS legacy electronics. Okay, and we would like to make brand new ones from scratch, essentially. Okay, of course we aim at using these modules because they can get to let's say 10-15 microns of resolution. Of course, the whole thing is complicated by the fact that you need to align properly these modules. They need to be tilted in order to increase the charge sharing between the individual pixels. Therefore, the tilting and all that needs to a lot of care. So the mechanical structure is also not straightforward. But the CHROMI people actually would like to join in they would join in our experiment. So at least the mechanics and the supports would be, let's say, made available by them. Okay. Then, of course, those are. I'm not talking about the ECAL because we are not yet set. But again, as I mentioned, there are some discussion about using a couple of towers of the CMS ECAL again. But of course, also the trigger and the DQ are very much relevant. So, as I said, as far as the drift tubes and the gems, we plan to read them out without the trigger, essentially. So, get the stream of data out of the detector and then process it. But for the pixel, of course, we do need a trigger. Okay, so the trigger also, in order not to, given the fact that essentially we have 5 or let's say of the order of 10 signal events per minute, you don't want to store, kilohertz of data, of megahertz of data. So a trigger is also useful in order to skim data away. Okay, if not synchronously with the data taking, maybe even in a quasi-online way. But for sure, for the pixel, we do need a trigger signal. In order to implement that, we plan at having one scintillator in front of the target, okay, attached to it, okay, essentially matching the shape of the target in order to capture only the positrons going through the target, okay. So that would basically lead to about a megahertz of trigger signal, okay, and that would be like the denominator for our acceptance estimation, okay. And then of course we would place also scintillators along, let's say, if you want to keep it simple, we can place scintillators along the negative beam line, let's say negative line, okay, because you expect the spent positron beam to go towards, of course, the positive side of after the magnet, let's say. So if you place, so the rate of particle or negative particles is expected, is actually, we measured it to be rather limited. So we place detectors scintillator, sorry, on the negative line, that would provide a rather clean triggering signal. So the DAQ, as I mentioned, we plan to read out at 40 megahertz 3 tubes in the gem, but as I said, we need to provide a trigger to the pixels. There, I don't want to get into the details, but the fact that the positrons might get to the pixel modules in a completely asynchronous way with respect to the clock, okay, and that actually cause some inefficiency, okay. So we need to figure out a way to recover that efficiency, okay. But there are discussions, I think, let's say, needs to be worked out, but it's doable. And then the event building can be done in a quasi-online mode, and again, I don't want to spend too much time on that. So I'm concluding just with the plan for, let's say, for year one, which, let's say, so I didn't mention that, but we expect this campaign of measurements to be performed in more than 1 year, okay? So 2 or 3 years, that would be the estimate of the time we expect. Of course, not the entire year. Let's say we would ask for like 3 weeks during summer or fall, in 2022, 2023, 2024, okay? So that's our idea, let's say 3 weeks of beam time per year, okay? So the idea is that the first year, I just described it as a setup which is extremely challenging, especially if it is not our main job. Everybody is busy with also other experiments, especially CMS in my case. But indeed, we do plan to have some time dedicated in order to put everything together, integrate the subdetector, synchronize the timing, calibrate it, and then align and check the stability over time. So all these kind of things, I think, are mandatory for the first time we're gonna get beam with the entire thing together. Okay. So if we manage to achieve all these things, then probably the first year we can also try to assess, to measure the first. To perform the first measurements concerning the E plus E minus to E plus or minus, so the differential cross section and intrinsic mu emittance. So the second year, we very likely we would need to redo the measurements and ameliorate the measurements that we have done the first year, and then also try other things. So we can try to chase true muonium, which even though we know that is very tough. But also trying target options like different length, depth, if you want, of the beryllium target, other light materials, crystals as well, and then possibly also study the spent positron beam. Okay, that would require for sure the calorimeter along the beam line. And again, the third year would be to let's say take over from whatever we got left from year 2, and essentially measure the energy spectrum of the photons producing the target. Okay, because that's yet another thing that LEMMA might be willing to get, meaning that regeneration of the positrons by means of the photons produced by the impinging positron beam in the target. Okay. Okay, so the whole thing is, so at least the reason why I got started with all that is because this is really just, if you want, a playground, an exercise, okay? But if you read the original paper by Manuela, Mario Antonelli, Pantaleo Raimondi et al., they actually sketched down numbers having in mind the SPS, okay? So if the SPS is somehow converted into electron-positron machine, okay, as they expect to do, let's say, as they propose to do in this conceptual design report, okay, the ESPS, okay, then LEMMA could actually, LEMMA test beam, I mean, the setup we proposed could actually be scaled in order to be the, if you want, the setup to be used in order to be used at such a demonstrator. Okay, so you might have heard that indeed that an intermediate step towards the muon collider is a demonstrator. Okay, So the baseline at the moment is to have a proton-driven demonstrator, but there is room. There is not impossible also to plan and a positron-driven demonstrator. In that case, what we aim at studying in our experiment would actually let's say would actually scale to such a demonstrator for the positron induced muon collider. Actually, if you read that ESPS paper, they are quoting the test, let's say what we propose explicitly. Okay, so that's not something that is just throw that on the room just for making noise. It's something that is actually based on concrete numbers. So in summary, I'm concluding here. We had some experience with such a setup. Let's say at the beginning it was a very low cost ones. I mean, in the past we got essentially just recycled devices just to assess the feasibility of such a measurement. Now we plan to have a campaign of measurements at the CERN North area. Okay, and the goal is to test the production mode at the base of the LEMMA scheme. I guess that you grasp the fact that the proposed apparatus is challenging, okay, from several points of view. The nice thing is that though, beyond being a playground, as I said, for several detector and DAQ and trigger developments that could be useful in other experiments, that thing could also be scaled to serve as a muon collider demonstrator, okay, or something like that, okay. So I'm done. I'm available for questions.
Thank you, Marco. That was excellent. So I was trying to see how we as a group could probably find projects where we could get involved. I think you pointed out various interesting areas where we could get involved, I suppose, but we have to think more about it. But I think that are general questions we can take now, but we can talk about specifics of where we could get involved and things like that later, if that's okay with you, on some other day. So let's take some questions now. Anybody? Well, all right. So let me start maybe. Oh, Fabio, go ahead. Fabio,
yeah,
go
so
ahead.
just because there was no questions at least yet. So no, I wanted just to point out that about the possibility to search for the true muonium, that would be very, very interesting. But I think that in that case we have to rethink the target region part of the experiment, because I think that the only way is to search for one of the states of the true muonium which decays in a plus and minus and lives for I think I don't remember exactly the lifetime, but order of picoseconds. So we need to find the detached vertex with respect to the interaction. So probably we need a very thin target and the system of measurement of the tracks very close to after the target. So maybe we have to rethink that part of the experiment if we want to look for this state. But it would be very, very interesting as an additional possibility for this experiment.
I was going to ask a question about this muonium thing as well. Does anybody have a calculation of the production rate for muonium?
But there is some paper made by Stambrowski with a different. I think he also assumed different energy beams, but not
that it would depend,
not with a positron beam with a 45 GeV or rest. Because another problem would be the energy spread when you have so unbalanced energy difference between the two beams.
Yeah.
So the calculation didn't leave so many hopes, but one can try to think if there is a way. Maybe we should talk again with Stan.
So the positron, the mu plus and mu minus are going to have basically the same boost, right? They're produced at rest, they're traveling in the same direction essentially, but the opening angle needs to be very small in order for the bound state to form. So you need to be very, very close to the threshold, which brings the cross section for production down. So it's kind of tricky, right?
Yeah, but not only, but the other point is that you don't see the two muons. You see the decay products, which are or two photons or two electrons.
Oh no, after
the main channel.
First it needs to form before it decays. So we need to see which is produced delayed with respect to the formation time.
Exactly, and you have to distinguish by the more common E plus and minus in plus and minus, or E plus and minus in gamma gamma. So
yeah, it's not easy.
And the only way I think is to look for the state that live enough so that you can measure a detached vertex. So so it should travel a bit. Otherwise, I think there is no way to distinguish from the Baba.
Yeah, because it's the same energy, right? It will have the energy.
You see plus and minus in plus and minus, what you see.
The thing is that you should actually get a peak in the environment distribution of the.
The peak is the energy of your beam, is within the resolution of the beam. So I don't know if you are sensitive enough, but okay, I don't know. We have to think. Of course, it's not for the first year, this, but.
But there are several other technical measurements that are interesting, right? We want to first measure the cross section for producing the muons, and you want to measure the beam divergence.
Absolutely. This is, I mean, the experiment, I mean, the true muon is could be an addition, but it's not our goal. I mean, our main goal is what Marco said very well.
Any other questions for Manuela or Marco? So I have a question for Marco from the simulations point of view. For whoever wants to get involved, it would be good to get access to some giant simulation, and maybe it requires adding new elements to it and so on and so forth. Is there a code base that we could get access to that we can play with and see if we how it looks like that we can?
Yes. So we do have a dedicated GMT setup. We have students. There is a student in Rome that actually there was first a researcher in Rome and then a student working on the GMT simulation for actually 2018 setup, but also they are setting it up also for the planned future test beams. We also have a dedicated Monte Carlo written by another colleague that is actually simulating, including all the effects, the E plus, E minus, to E plus, E minus dynamics. Okay. So, but the GMT setup is there, and all let's say all the volumes are somehow let's say described by hand, in a sense that they didn't take whatever was already done in CMS, even though most of these detectors have already geometry implementation within the CMS software. So one possible improvement is actually to let's say redefine the old setup as an XML file to be used for in the CMS software, let's say, because indeed all the components, most of the components are done that way, and I think Nicola might comment better than me because he's an expert in those things. But I think one of the goals that we have is indeed try to go in that direction. So let me summarize. And simulation in GMT exists. Data sets have been produced as well. An improvement which would actually also simply, let's say, ease a little bit the overall implementation for sure of the reconstruction software is to port that to the actual CMS framework to some extent. which would allow it to use the actual description that is used for those subdetectors.
Okay. Nicola, do you want to comment, or should we talk about it?
Can you hear me? Can you hear me?
Yeah.
Okay. So because I have to move to my port to my phone. Yeah, I think what Marco is referring to is having something which can be plugged in also not only on the simulation but also on the reconstruction side, and I think this has been done. I know it has been done for this Chromie setup already. Because they had their own reconstruction, and by doing that they could reuse CMS software for example, alignment purposes and reconstruction, which I think is necessary when we go to such a complication. We don't want to rewrite everything from scratch, including all tracking, which would be quite difficult given the kind of detectors we plan to have. So I think that the goal there would be to work on not specifically only on the GEN part, but really on being able to import all this setup in the CMS framework of specifically for reconstruction, starting from the geometry, from the XML geometry to the full reconstruction, which is quite some work, I think, but it's not impossible to do. I think this is an area where we really need quite some work, and it's of course an advantage to have all detectors which are somehow connected already to CMS. The only thing which is non-standard is probably the 10 by 10 gems, which are custom made, but they are being used now already in a gem, in a test beam, basically to as a telescope for other gems, for CMS gems. So they are already working on it.
So the back-end electronics for this, the front end is part of the same thing as what we're doing for the station 1 gems, right? And you're using for the back end the micro TCA electronics. Is that right?
I don't know the details for the gems specifically, but I think so.
I think that Chromie also uses micro TCA electronics, right, from phase 1. Okay.
Yeah, but Marco may comment better on what is the plan to for the readout of that.
Mm-hmm.
Okay, I must say that the actual plans for the readout is under development. Actually, we are, as I said, we given the fact that we didn't manage to let's say to schedule the test beam this year, we gathered only the general information concerning the possibilities for the value detectors, and the gems are used in another in RD51, whatever it is, and they are used. Let's say they are read out with the similar technologies as we are using at the moment, meaning like an FPGA board on the PCI Express bus of.
These are the ferrules or something.
Right?
This is the ferrule or whatever they're calling, right?
It's the CVP13 board, Sridhara.
Oh, I see.
We're working on this, so it's the CVP13 we're using at this moment to read this out. Okay.
All right.
Yeah, so exactly. I mean, I'm not fully aware of the actual system they're using, okay, but we do believe that putting them together, integrating the two, is not such a big deal. Whereas for the pixels, instead, we should, let's say, our main worry is concerning the pixel, because, as I said, there either we go for re-implementing the let's say the legacy electronics used in phase 1, let's say recovering boards here and there and putting them together, but we actually would much prefer to redo things essentially from scratch. That would actually very much be appreciated by the tracker community, and and they told us that they would give support in that terms, in terms of that. But indeed, as far as the GEM are concerned, I'm not.
For phase 2 pixel readout, Cornell Group is building some boards, and it's not quite ready yet. So I don't know how one could use phase 2 things. But the phase 1 boards, the AMC13 that you were referring to in the micro-TCA crate, plus some other board is needed to actually process the output from the electronics. AMC13 just integrates it and delivers to the PC. But you do need some other board to do that. So there's some amount of work there. I think that the Imperial guys have designed boards for that, for the tracker in the past for phase 1. For phase 2, I think that the Cornell Group is working on it for at least for the pixels. I don't know about the inner tracker. Okay, so I'll try to find out a little bit more about that if there is any interest in getting involved.
I mean, just to comment, Sridhar, I mean, looking at the picture that they had of the gems, and it looks very much like the GE11 setup of having the same front end electronics and and also Anna was, name was there. So it looks very much like basically a copy or a smaller version of what we're using in CMS.
Yeah, Kevin, it is.
Yeah,
it is. Yeah. There's a smaller version of GE11. Yeah.
Yeah.
Okay.
I mean,
so Kevin is now essentially in charge of the electronics for the GEM. So
yeah. I mean, so actually, the group here also, Peter is doing the integration of that, and Camilla is writing the DAC software for it. I mean, so I think that is a natural place, because I think it looks like it just it was essentially the same thing. So that could be adapted, I would guess.
Yeah. So from the GEM point of view, we have Kevin, Peter, and Camilla who could contribute. Carl's connected, and Carl Boscolo did the DD for HEP migration of the CMS offline software setup, and he is setting up, I think, right now the run 3 configuration. So yeah, there's a possibility of getting involved there. I had a slightly different question though. So most of the scientists and senior people are divided in various ways. Are there people who are available to guide new people, students in particular, to do work on this type of things? I think it would be great for students to be involved in an experiment right from the start and learn about how the detectors work and how we put together the readouts and all of that right from the front end. I think it's a wonderful project for somebody to be involved there rather than just do some analysis from after the data is collected in CMS. Do you have postdocs who are full-time working on this, or part-time based at some?
Are you asking me, Sridhar? Sorry.
Yeah, I don't know if there are people who.
Yeah. I mean, we have actually, as I was telling you when we chat the other time, this is extremely appealing for students. I mean, I'm actually having more students coming for, let's say, asking for thesis work or something like that, for this kind of activity rather than CMS. Because indeed, as you said, I mean, they feel like they would be much more, let's say, connected to the actual work of, and the actual experiment itself. And they feel like they would experience the whole process from, let's say, the design to the actual operation, and let's say setting up and operating the experiment, and then the analysis at the end. So we do have a couple of PhD students, and there are postdocs, okay, not in Padua, but in Milan. So there is a bunch of youngsters that are actually involved in all these things. So as I said, there were in the past. Nowadays, indeed, I mean, we still have to resume activities in view of the actual test beam, let's say the actual experiment next year, because indeed, I mean, we got a little bit, let's say, on hold during the pandemic, given the fact that we didn't have the chance to go to CERN and to meet in person, so on and so forth. And for these kind of things, those, you know, the meeting is kind of relevant indeed. But indeed, there is you know, the community is rather young on average, and indeed, I mean, there's plenty of work that can be tackled by young enthusiasts.
Thank you, Marco. Thank you, Manuela. It's been a little bit longer than we planned, but it was very, very useful.
Sorry about that.
Yeah, very useful for us. So thank you for also agreeing to record things. So for those who missed it, they can look at it. Perhaps we can organize a meeting with those who want to get involved as a separate meeting at some point on Zoom, if it is okay with you. Primarily for Marco,
whenever you want. I mean, we can also enlarge a little bit of discussion with other people that work on the test beam on our side. So whenever you feel like, just ping me or Fabio or Nicola, and let us know.
Okay, great. Thank you. So for the second part, for Manuela, thank you also for giving the overview talk of about the LEMMA scheme and all of that. So we'll, if there are questions, there will be more of them coming by email. Okay.
Very good. Thank you.
We'll close the meeting at this stage. Thank you all. Bye.
Thank you very much. Bye, everybody.
Thank you very much. Bye bye.
Ciao. Ciao. Ciao.
Ciao.
Bye. We owe you a dinner at some point.